Welcome, deep divers, to Antarctica, a place of, well, raw, captivating beauty and truly unimaginable danger.
It really is.
Picture this vast white wilderness. It's been a stage for incredible human ambition, for groundbreaking scientific discovery, and sadly, for profound, heartbreaking tragedy.
And over a century later, the story it holds still echoes, doesn't it? With lessons and sort of lingering questions.
Absolutely. It's a story that truly captures the imagination, revealing so much about the limits of human endurance.
It really does. Today, we're taking a deep dive into the British Antarctic Expedition of 1910-1913, famously known as the Terra Nova Expedition, led by the renowned Captain Robert Falcon Scott.
Scott's primary goal was clear, wasn't it? To be the first to reach the geographic South Pole.
It was the headline, yes.
But, and this is crucial, I think, it wasn't just about planting a flag. He also harbored this deep ambition to continue and expand upon the significant scientific work he'd begun on his earlier discovery expedition.
Exactly. So a dual mission, a race, yes, but also a massive scientific endeavor woven into it.
A race, as history tells us, he didn't actually win.
No. He and 4 companions did reach the pole in January 1912, which was an incredible feat of human will in itself.
Absolutely monumental.
But they found they'd been preceded by a Norwegian team led by Roald Amundsen. He'd arrived 34 days earlier.
Ouch. And then, tragically, Scott's entire polar party perished on the return journey.
Yes, the whole group.
It's one of those historical narratives that just, it grabs you. We're going to uncover the meticulous preparations, the unexpected rivalries that added fuel to the fire.
There's definitely some tension there.
The innovative and sometimes deeply flawed strategies they employed, the brutal realities of Antarctic survival, and the enduring scientific legacy that emerged from this ill-fated venture.
Right, because there was a legacy, despite the tragedy.
Why did this expedition, filled with such promise, end in such devastating loss? What does it teach us about leadership, ambition, and, well, the unforgiving power of the world's coldest continent? Let's unpack this.
Sounds good.
Okay, let's cast our minds back to the early 1900s. Scott had already led the discovery expedition, reached a new farthest south at 82 degrees 17 meters out, and made significant contributions. But the pole itself remained unconquered. What was it that really drew him back for a second attempt?
Well, the Antarctic was calling, definitely. But so was, I think, intense personal and national pride. In 1909, Ernest Shackleton's Nimrod expedition had come incredibly close to the pole, less than 100 miles away.
Right, Shackleton, his former subordinate.
Exactly, and that created a new benchmark for British Antarctic exploration. More than that, Shackleton had used McMurdo Sound, an area Scott considered his sort of field of work from his previous expedition.
Ah, so a bit of territoriality there.
You could say that. It definitely soured relations and, I think, intensified Scott's ambition to surpass Shackleton.
But the personal rivalry wasn't the only pressure, was it? What was the broader context? This was turning into a truly global race for the pole.
Oh, absolutely. Scott was keenly aware that other nations were eyeing the prize. German, Japanese, Australasian expeditions were all being planned or talked about.
A lot of activity.
And then there was the elephant in the room, Roald Amundsen. Amundsen had initially announced an Arctic voyage, but then very quietly pivoted his whole expedition south.
Sneaky.
Well, strategic, perhaps. Scott knew this was a global competition, and the stakes were incredibly high for Britain.
To tackle such a monumental challenge, Scott needed a formidable team. Tell us a bit about the people he brought together.
He truly did assemble an impressive group. From 8,000 applicants, he selected 65 men. It was a blend of seasoned polar veterans, some Discovery alumni, and even some who'd sailed with Shackleton.
Interesting mix.
Yeah. Think of critical specialists like Lieutenant Edward Evans, his second-in-command, and Captain Lawrence Oates, an Army captain known for his oarsmanship. He famously volunteered 1,000 pounds of his own money and his services.
Wow, that's commitment.
Absolutely. And the lower deck included tough, experienced men like Edgar Evans and Tom Crean, who really knew polar survival inside out.
But this wasn't just about physical endurance, was it? The scientific ambition was equally huge.
It was immense. Edward Wilson, known affectionately as Bill, was the chief scientist and Scott's closest confidant. A qualified doctor, a distinguished zoologist, and a talented illustrator.
A real polymath.
Pretty much. His team was considered perhaps the most impressive group of scientists ever assembled for a polar expedition at that time. Top minds in meteorology, physics, geology.
So a proper scientific mission running parallel to the pole attempt.
Exactly. And then there was Apsley Cherry Garrard, He wasn't technically a scientist, but he contributed significantly financially too, and would later become the expedition's interpreter and conscience through his writing. This was discovery on every level.
And financing this whole thing. It was a private venture, right? Not like the Discovery. That must have added another layer of complexity.
Absolutely. Unlike the Discovery expedition, this wasn't institutionally funded by the Navy or Royal Society in the same way. The estimated cost was substantial, around £40,000.
A huge sum back then.
Massive. Half came from a government grant, but the rest had to be raised through public subscription and loans. Commercial firms did help out, generously providing free provisions.
Still, a lot of fundraising pressure on Scott.
Definitely. And to maintain order and flexibility, Scott even leveraged his Royal Yacht Squadron membership. This allowed him to impose strict naval discipline and, crucially, sidestep some standard merchant shipping regulations. It gave him greater control.
So, on one hand, Scott's public appeal stressed the South Pole first, the glory, the race for Britain.
That was the big selling point.
But then you have Wilson, the chief scientist, believing the scientific work was the true main objective. He even said, "No one can say that it will have only been a pole hunt." Sounds like a delicate balance.
It absolutely was. Their scientific plans were incredibly ambitious, studying the emperor penguin colony at Cape Crozier, extensive geological, magnetic, meteorological studies, exploring uncharted lands.
So Scott was selling the dream of national glory.
While Wilson was quietly building this foundation of profound scientific understanding, a fascinating dynamic.
Now let's talk about the initial strategy, because this is where some of the expedition's vulnerabilities might have started to show. Scott decided on this mixed transport strategy: motor sledges, ponies, and dogs.
Right. The idea was to use the motors and animals to ferry supplies across the Great Ice Barrier, the flat part, preserving human strength for the really tough man-hauling part further south, up the Beardmore Glacier.
Okay, sounds reasonable on paper. How did it work out?
Well, this mixed strategy, which seemed sort of prudent, quickly revealed a crucial lesson for extreme environments. Complexity often introduces fragility. The motor sledges, for instance, which were quite innovative for the time.
I hopes for those.
Yes, but they proved only briefly useful, failing after little more than 50 miles. A stark reminder that new tech can really falter in the harshest proving grounds.
50 miles. That's barely getting started. And the ponies. I understand they had their own set of issues.
They did. Lawrence Oates was in charge of them, a very capable horseman. But the initial purchasing had been done by Cecil Mears, who knew dogs but apparently little about horses.
Uh-oh.
Yeah, leading to poor quality animals, some too old. And critically, Norwegian snowshoes for the ponies, which could have really helped them on the soft snow, were left behind at the base. Oates wasn't happy about that.
So, problems with the motors, problems with the ponies. What about the dogs?
Scott was initially dubious about dogs, based on his discovery experience where they hadn't performed well. He later came to recognize their effectiveness, especially in skilled hands like Mears, but he still leaned heavily on this complicated, multi-pronged approach rather than Amundsen's single-minded focus on dogs.
Which, in hindsight.
Exactly. Arguably, this mixed strategy, rather than committing fully to one method, was a critical vulnerability from the start.
The journey to Antarctica itself was also fraught with early difficulties, wasn't it? Even before they landed.
It really was. The Terra Nova sailed in June 1910. Scott, still fundraising, joined later in South Africa and Australia.
And it was in Australia he got the news.
In Melbourne, yes. That bombshell telegram from Amundsen, simply, "I'm going south."
Just like that.
Wow.
How did Scott react?
Publicly, he put on a brave face, said his plans wouldn't change, emphasized the science. But his private diary revealed he knew Amundsen had a fair chance of success. The pressure ratcheted up instantly.
And the ship itself had problems.
Oh, yeah. The Terra Nova, already overloaded, got hit by a severe storm. They lost 2 ponies overboard, a dog, significant amounts of coal and petrol. Then they were delayed for 20 crucial days by heavy pack ice getting south, consuming even more of their precious coal.
Not an auspicious start.
Far from it. Setbacks before they even properly began.
So they finally arrive in January 1911, establish their base at Cape Evans, which was a bit north of Scott's old Discovery hut.
Right, about 15 miles north. They got the prefabricated hut up pretty quickly, though they did lose one of the 3 motor sledges during unloading when it broke through the sea ice.
Another loss. And then came the truly shocking news from Campbell's party.
Yes. Campbell's Eastern Party, originally sent to explore King Edward VII Land, sailed east and unexpectedly encountered Amundsen's expedition already camped at the Bay of Whales, a deep inlet in the ice barrier.
Right on the barrier itself. A different approach.
A much more southerly starting point than Scott's. Amundsen was apparently courteous, even hospitable, but Campbell had to return and report this. The news was devastating back at Cape Evans.
How did Scott's team take it?
Terry Garrard wrote that some initially wanted to sail over and have it out with the Norwegians. But Scott calmed things down. His diary entry was stoic. To go forward and do our best for the honor of our country without fear or panic. But the race was undeniably starkly on.
Despite that shock, the critical task of laying food and fuel depots for the polar journey had to begin. They aimed for the big one, 1-ton depot, at 80 degrees south. How did that go?
It began, according to Terry Garrard, in a state of hurry bordering on panic. Progress was slow, partly due to those pony issues we mentioned. The lack of snowshoes really hampered them.
And Scott made a change.
Yes, concerned about the pony's condition and the time it was taking, Scott made a fateful decision. He decided to lay 1-ton depot at 79 degrees, 29 hours south.
So short of the planned 80 degrees S mark.
Over 30 statute miles short. It might have seemed like a minor adjustment under pressure, but that shorter distance would have catastrophic implications on the return journey.
Hindsight is brutal. And the depot laying trip itself wasn't without loss either.
No, the early losses mounted. 2 ponies died returning to base from the depot trip, and then 3 more died tragically when the sea ice they were on broke up near Hut Point. Of the 8 ponies that started that journey, only 2 returned. Their animal transport capability was significantly diminished even before the main polar journey began.
After all these early setbacks, the long Antarctic winter descended. April to August, months of darkness. How did the team cope with that isolation down at Cape Evans?
Well, maintaining physical and mental well-being became absolutely paramount. The hut was ingeniously divided by a wall of packing cases, separating the officers and scientists from the men, but everyone had vital roles.
Keeping busy was key.
Essential. Daily exercise for the surviving ponies. Meticulous dog care. Scott himself spent ages painstakingly calculating sledging rations, trying to get the balance perfect. Intellectually, they kept stimulated with lectures, ponting on Japan, oats on horse management, debenham on volcanoes.
That's quite academic.
They even played football on the ice and revived the expedition's own newspaper, the South Polar Times. It was a structured, rigorous routine designed to keep spirits high and minds sharp through the polar night.
But the winter also brought one of the most incredible feats of endurance in polar history.
Yeah.
The worst journey in the world. Tell us about that.
Yes. That phrase, coined later by Apsley Cherry Garrard in his book, truly encapsulates it. Dr. Edward Wilson, Henry Bertie Bowers, and Cherry Garrard himself undertook this daring winter journey to Cape Crozier.
In the dead of winter. Why?
Its primary purpose was scientific, to collect emperor penguin eggs at a very early embryo stage for developmental study. Wilson had started this research on the Discovery Expedition and wanted to get eggs fertilized earlier in the season.
Okay, so a specific biological goal.
Right. But critically, it was also a field test, a way to trial their rations, clothing, and equipment for the upcoming polar journey under the absolute most extreme conditions imaginable.
And what conditions they were. We're talking Antarctic, midwinter darkness, and cold.
Unbelievable conditions. Imagine traveling in near total darkness, facing temperatures plunging to a mind-numbing 77 degrees Fahrenheit below zero. That's minus 61 Celsius.
Just saying, it makes me shiver.
Terry Garrard famously called it 109 degrees of frost, a term that barely captures the brutal reality. Their gear, their clothes, their sleeping bags were constantly frozen solid, their teeth cracked from the cold.
And they faced more than just cold, didn't they?
Oh, yes. They managed to build a small stone igloo near the penguin colony and collect a few precious eggs. But then a Force 11 blizzard hit them. It ripped the roof off their shelter and completely carried away their tent.
Lost their tent. And that's a death sentence.
Miraculously, after days searching in the dark once the storm abated, they found the tent wedged in some rock some distance away. Pure luck.
Incredible. They returned on August 1st, having survived. What did Scott make of it?
Scott hailed it as a very wonderful performance. He was particularly satisfied with how the equipment and rations had held up. Scientifically, the eggs didn't quite prove Wilson's specific theories, but the journey itself.
So what does this all mean? This epic test of endurance, though maybe inconclusive in its primary scientific goal, proved vital for preparation and showcased just extraordinary human resilience, didn't it?
Absolutely. It's a stark testament to the human spirit pushing far beyond perceived limits, all in the service of discovery and, preparing for the main event, the ultimate field test.
While the main party endured the winter at Cape Evans, other teams were out making their own contributions, often facing their own hardships. Campbell's Northern Party, for instance, after that encounter with Amundsen.
Right, their plans changed. They ended up exploring further north along the coast of Victoria Land. But the Terra Nova couldn't pick them up as planned at the end of the summer season due to heavy pack ice.
So they were stranded.
Effectively, yes. They were forced to spend a harrowing winter in a cramped snow cave they dug on Inexpressible Island. They suffered severe privations, frostbite, dysentery, starvation, extreme winds, living off seals and penguins cooked on a blubber stove.
Sounds horrific.
It was. But they survived, showing incredible grit, and ultimately self-rescued the following spring, trekking hundreds of miles back to Cape Evans.
Amazing resilience. And there were also the Western Geological Parties, led by Griffith Taylor.
Indeed. Taylor's teams conducted 2 extensive geological expeditions, mapping and exploring coastal areas west of McMurdo Sound, including the remarkable dry valleys, places that look almost Martian.
Crucial scientific work.
Absolutely vital. They collected geological specimens, charted new territory, pushed the boundaries of scientific understanding of the continent's history. They also faced their own challenges, including delayed pickups by the ship and having to undertake long, arduous treks themselves. The scientific output from all these side expeditions, despite the hardships, was truly immense.
Okay, so winter ends. The satellite parties have done their work, often under duress. Now, the time finally comes for the main event, the dash to the South Pole itself. Scott's plan involved 16 men initially, didn't it?
Yes, a large support structure. Using the motors, ponies, and dogs to haul supplies as far south as possible, specifically to the base of the Beardmore Glacier. Then support parties would turn back at stages.
And the dogs had a specific role on the return.
This is critical. Scott explicitly ordered the dog teams, driven by Mears, to return south later in the season to meet the returning polar party around March 1st, somewhere between latitudes 82 degrees and 82 degrees 30 south. The idea was to hasten the return journey off the polar plateau.
A crucial safety net, essentially.
That was the intention. But as we know, the strategy started to unravel almost immediately.
The motor sledges again.
Both remaining motor sledges broke down after only about 50 miles on the barrier. This forced the men to start man-hauling the heavy sledge loads much earlier than planned, hundreds of pounds per sledge, relying solely on human strength for an extra 150 miles. Brutal work.
And the ponies.
They performed as well as could be expected, but struggled in the soft snow and cold. They were shot as planned at the gateway to the Beardmore Glacier, their meat cached in depots for the return journey. The dogs, having hauled supplies that far, returned north with Mears and the Russian dog driver Dmitri.
Did Mears send any word back?
He carried a message from Scott back to base camp. It apparently noted that things were not as rosy as they might be. An understatement, perhaps.
So they ascend the massive Beardmore Glacier, man-hauling all the way. Then, on January 3rd, 1912, way up on the polar plateau at 87 degrees 32 minutes south, Scott made his final, fateful decision about the composition of the polar party.
Yes. He decided to take 5 men to the pole, himself, Wilson, Oates, Bowers, and Petty Officer Edgar Evans. Not the 4 he had originally planned for.
Why 5? Bowers wasn't initially planned for the final group, was he?
No, Bowers was added almost as an extra man. Scott seemed impressed by his endurance, but taking 5 meant a complete last-minute recalculation of rations, fuel, and tent space, all of which had been meticulously planned for 4-man teams.
That must have caused logistical issues.
Potentially significant ones. Lieutenant Teddy Evans, William Lashley, and Tom Crean, the last support party, were then sent back, heartbroken not to be going all the way.
So the final 5 press on. They passed Shackleton's furthest point.
On January 9th, yes, a milestone. But the psychological blow landed 7 days later, on January 16th. They spotted something dark on the horizon.
Not a natural feature.
No, it was Amundsen's black flag marking his route. Then they found his tent, Polheim, at the pole itself on January 17th. Inside was a note confirming his arrival on December 14th, 1911, 34 days earlier.
Utterly crushing.
Scott's diary entry captured his desolation. Great God, this is an awful place, and terrible enough for us to have labored to it without the reward of priority. The discovery just drained them.
The grueling return journey began, now without the prize. Just the struggle for survival. And it quickly turned desperate.
Yes. Edgar Evans, the physically strongest man, began to deteriorate rapidly. He suffered severe frostbite on his hands and face, had a nasty cut on his hand that wouldn't heal, and possibly suffered a head injury from several falls on the glacier ice.
And he didn't make it back to the barrier.
No. Near the foot of the Beardmore Glacier, he collapsed and died on February 17th, a huge blow to the team's morale and strength.
Yet, even amidst this unfolding tragedy, there was a remarkable moment of scientific dedication.
Incredible, isn't it? While descending the Beardmore, in a brief respite from the struggle, Scott allowed Wilson, the geologist as well as doctor and artist, to stop and collect about 30 pounds of fossil-bearing rock samples.
30 pounds? That's a lot of extra weight to haul when you're starving and exhausted.
An immense burden. But think about this. In their dying weeks, enduring unimaginable suffering, Wilson collected these Glossopteris plant fossils. These weren't just rocks, they were the silent witnesses found with their bodies later.
And their significance.
They provided crucial evidence supporting the then revolutionary theory of continental drift, showing Antarctica was once connected to other continents, a profound scientific legacy literally carried to their deaths.
An astonishing detail. But the real turning point, the point of perhaps no return, came when they reached the planned rendezvous area for the dog teams.
Right. They reached the latitude of 82 degrees 30 minutes south, where they expected to meet the dogs, actually 3 days ahead of the March 1st schedule Scott had set. But the dogs were not there.
Just empty snow.
Empty, endless snow. Scott noted a horrid element of doubt creeping into his diary. They were now facing this terrible triple threat. The non-appearance of the crucial dog teams, a sudden, unseasonable, and dramatic drop in temperatures.
How cold are we talking?
Down to minus 30 Fahrenheit during the day, plummeting to minus 47 Fahrenheit at night, far colder than they had anticipated or experienced on the way south. And thirdly, a critical shortage of fuel, particularly paraffin, in the depots they reached. They found the fuel tins were not full due to evaporation or leakage in the extreme cold.
So, colder than expected, less fuel than expected, and no dogs to speed them up.
Exactly. The extreme cold also changed the snow surface, creating these horrible woolly crystals that caused immense friction under the sledge runners, making progress agonizingly slow. It felt like pulling through sand.
And the physical toll was mounting, particularly on Oates.
Yes. Captain Oates' feet were terribly frostbitten from an old war wound aggravated by the cold. His hands, too. He was slowing the party down and knew it. His feet and hands became, as Scott wrote, pretty well useless.
Which led to his famous sacrifice.
On March 16th, possibly his birthday, knowing he was a burden and perhaps hoping his death might give the others a slim chance, he voluntarily left the tent during a blizzard, uttering those now legendary words, "I am just going outside and maybe some time." He walked out into the blizzard to his death.
An incredible act of self-sacrifice.
Truly. Scott, Wilson, and Bowers struggled on for a few more days, pushing northwards. They got agonizingly close to the next big supply cache.
How close?
Just 11 miles south of One Ton Depot. The depot that had been laid 30 miles further north than originally planned.
Those 30 miles.
Those 30 miles might have made all the difference. But there, just 11 miles short, a fierce, prolonged blizzard trapped them in their tent from March 20th onwards.
Perfect.
Completely pinned down, unable to travel, supplies exhausted. Scott's last diary entry is dated March 29, 1912. It sums up their desperate plight. "We shall stick it out to the end, but we are getting weaker, of course, and the end cannot be far. It seems a pity, but I do not think I can write more. Our Scott, last entry, for God's sake, look after our people."
Chilling. Just absolutely chilling words.
It's truly a heart-wrenching end, and the lingering question, the one debated ever since, remains. With all their preparations, with all their ambition and experience, what exactly went wrong? How did it come to this?
Okay, let's try and unpack this because it's complex. Recent discoveries, particularly research highlighted by Karen May in 2012, really emphasize a critical detail we touched on. Scott had left explicit written orders back in October 1911.
The orders for the dogs.
Exactly. For the dog teams to meet the returning polar party around March 1st, specifically between latitudes 82 degrees and 82 degrees of 30 imbeaux south, May calls this a vital order. And ultimately, it was not carried out.
Right, and the reasons why it wasn't carried out form this complex chain of decisions, circumstances, and maybe some bad luck.
If we connect this to the bigger picture, it wasn't a single point of failure, was it? It seems more like a devastating cascade.
I think that's a good way to put it, a cascade. It involved miscommunication, maybe some differing interpretations of orders under pressure, resource shortages back at base, and incredibly difficult decisions made by the men left behind.
So what happened with the dog teams? Cecil Mears, the main dog handler.
Mears returned to base with the dogs in early January, as planned, after supporting the polar party onto the glacier. But he seemed keen to leave the expedition and return home on the ship. Some accounts suggest he was disgusted or preoccupied. He also reported that the dog food supplies left at One Ton Depot were insufficient for a long journey south.
Okay, so Mears is maybe not fully engaged, and there's a supply issue. Who's in command back at Cape Evans?
Surgeon Lieutenant Edward Atkinson was left in command. Initially, the shore party was heavily involved in the very arduous task of unloading supplies from the returning Terra Nova ship in late January and early February. This delayed preparations for any relief journey.
Priorities.
Atkinson did eventually set out south with dog teams on February 13th, but he didn't get far before he had to divert. Why? To rescue Lieutenant Teddy Evans, the leader of the last returning support party, who was found critically ill with scurvy near Corner Camp.
Ah, the rescue involving Tom Crean's solo walk.
That's the one. Crean made a heroic 35-mile solo trek back to Hut Point for help. Evans was safe, but this rescue effort pulled Atkinson and the dog teams off their original course and used up valuable time and resources.
So Atkinson returns to Hut Point with the sick Evans. What next?
He was now faced with dwindling time and resources. Instead of going himself, he sent Apsley Cherry Garrard, who was willing but inexperienced and very short-sighted, out with the dogs and Dmitri, the Russian driver.
But not to the original rendezvous point.
No. And this is crucial. Atkinson instructed Cherry Garrard to travel only as far as One Ton Depot at 79 degrees 29 Arabites to resupply it and wait for Scott there, effectively canceling Scott's explicit order for the more southerly rendezvous between 82 degrees and 82 degrees 30 ROS.
Why would Atkinson change Scott's order?
Atkinson later claimed Scott had given him discretion. He also stressed to Cherry Garrard that the dogs were precious and not to be risked beyond One Ton Depot, citing the need for them for the following season's scientific work. Karen May suggests this instruction about not risking the dogs might have been Atkinson's own justification after the fact.
So Cherry Garrard goes only to One Ton Depot.
Yes, he reached it, deposited the supplies, but then faced severe weather himself. His dogs were weakening, supplies were running low. He waited there for Scott for several days beyond when Scott might have been expected.
He must have agonized over whether to push further south.
Absolutely. But bound by Atkinson's orders not to risk the dogs, feeling ill-equipped for a longer, unsupported journey, and seeing no sign of Scott, he made the torturous decision to turn back on March 10th.
And how far away was Scott's party at that point?
Unbeknownst to him, Scott's dying party was struggling just 70 miles further south. Cherry Garrard was haunted for the rest of his life by thoughts of what he might or should have done differently.
A terrible burden to carry. Did Atkinson try again?
Yes, Atkinson made one final attempt himself, setting out with leading seaman Keohane on March 26th. But they only got as far as Corner Camp before turning back, concluding, likely correctly by that late date, that the polar party must have perished in the unusually severe autumn weather.
So it's this tragic combination of factors.
Exactly. It's a complex interplay. Scott herself, in his final message to the public, sought to deflect blame, writing, "I do not think human beings ever came through such a month as we have come through. No one is to blame, and I hope no attempt will be made to suggest that we have lacked support."
A noble sentiment in the face of death.
And Cherry Garrard later reflected, summing up the endless what-ifs, that the whole business simply bristles with ifs. If the depot had been further south, if the weather hadn't turned so viciously cold, if the dogs had made the rendezvous, if Evans hadn't gotten scurvy, so many factors.
After the winter, a search party set out the following spring.
In October 1912, yes, led by Atkinson. On November 12th, they found the tent, partially buried in snow, containing the frozen bodies of Scott, Wilson, and Bowers, just those 11 miles south of One Ton Depot.
And Scott's diaries?
They were found with him. They revealed the full, devastating story of their journey, their success in reaching the pole, and their desperate final struggle. The search party built a large snow cairn over the tent and bodies, topped by a cross-fashion from Trigg brand skis.
Oates' body was never found.
No, just his sleeping bag was found sometime later. He walked out into the white wilderness.
How was the news received back home, and how has Scott's reputation evolved?
Initially, and for decades, Scott was hailed as an unparalleled tragic hero in Britain. His stoicism, his message to the public, resonated deeply. The focus was on the heroism and sacrifice.
But that changed.
Yes, starting around the 1970s, particularly with Roland Huntford's controversial biography, more critical views emerged. Huntford strongly questioned Scott's leadership, planning, and competence, contrasting him very unfavorably with Amundsen.
So a backlash.
A significant one. However, in more recent decades, subsequent works like biographies by Ranulph Fiennes and David Crane, Susan Solomon's scientific analysis of the weather conditions, and Karen May's work on the orders have re-examined the evidence. They tend to offer a more nuanced picture, acknowledging Scott's flaws perhaps, but also emphasizing the unprecedentedly severe weather conditions, the role of misfortune, and the complex chain of events that led to the disaster. The view now is generally more balanced.
So what does this all mean for us today, looking back? The Terra Nova Expedition stands as this profound testament to human endurance, certainly scientific ambition, but also the brutal, unforgiving power of the Antarctic.
Absolutely. It's a story of incredible personal bravery, you can't deny that. Meticulous planning in many respects, but also, as we've discussed, a series of unfortunate events, perhaps questionable decisions under pressure, and factors beyond their control.
And while the tragic loss of life overshadowed so much for so many years, the expedition's scientific contributions were truly immense, weren't they?
They really were, often overlooked in the popular narrative focusing on the race, but the 12 scientists on board the largest Antarctic scientific team of its time made hugely significant discoveries across zoology, botany, geology, glaciology, and meteorology.
What kind of discoveries?
They returned with over 2,100 biological and geological specimens, 400 of which were completely new to science at the time.
And those fossils?
And crucially, those Glossopteris plant fossils, collected by Wilson in their final desperate days, provided that key evidence for continental drift. Plus, the expedition yielded the longest unbroken meteorological record from the Antarctic interior during the early 20th century. This data profoundly shaped our understanding of the continent's climate and weather systems.
So the science, which Wilson believed was the main purpose,
Left an indelible mark. It directly led to the founding of institutions like the Scott Polar Research Institute at Cambridge, which continues vital polar research today. The scientific legacy is huge.
even the expedition's namesake ship, the Terra Nova, had a long life after the expedition.
It did. It continued working, mostly sealing and supply work in the Arctic and North Atlantic, for another 30 years before finally sinking off the coast of Greenland in 1943 during wartime service. Its wreck was actually discovered on the seabed in 2012.
Wow. A final echo of the expedition.
Indeed.
So listening to this story, the Terra Nova expedition forces us, I think, to confront some difficult questions. When operating at the absolute limits of human capability in these extreme environments, how do we weigh the pursuit of grand goals like being first to the pole against the inherent risks to human life?
It's a fundamental question in exploration, isn't it?
And in the face of these insurmountable natural forces, like that unexpected killer cold snap, where does the line between heroism and perhaps hubris truly lie? What choices, if any, do you think could genuinely have changed that tragic outcome? And maybe more broadly, what does this whole story tell you, our listeners, about the unpredictable nature of exploration, even when undertaken with the best intentions and the most meticulous planning imaginable?
A lot to think about there. The ifs definitely linger. What if I told you that nothing is actually, well, one of the most fascinating and complex concepts in the universe? It sounds simple enough, right? Just empty space. But if you've ever really stopped to think about it or, tried to create it, you find out nothing is far from simple. Today, we're taking a deep dive into the concept of vacuum. We've got a fantastic source here, the Wikipedia article on vacuum, and it gives a really comprehensive overview of this mind-bending topic.
Absolutely. And our mission today is basically to unpack what a vacuum truly means. We'll look at everything from its ancient philosophical roots right up to its cutting-edge role in quantum physics. We'll explore how we measure it, how we use it every day, even its kind of surprising effects on living things. You might just find that this empty space is, well, it's pretty much everything but empty.
Okay, let's start at the very beginning then. When we talk about a vacuum, what exactly are we talking about in, simple terms?
Well, at its absolute core, a vacuum is just space devoid of matter, really truly empty. But in practice, it's more of a spectrum. We often think about an ideal or perfect vacuum, sometimes called free space, where there are absolutely zero particles. That's mostly theoretical, though. What we actually create and work with are partial vacuums.
Zero vacuums.
Yeah, regions where the gas pressure is just significantly lower than the air pressure around us, atmospheric pressure.
So it's more about degrees of emptiness then, like how empty can these partial vacuums actually get? Can you give us a sense of that scale?
Yeah, absolutely. The quality of a partial vacuum is basically measured by how much stuff, how much matter is left. Your everyday vacuum cleaner, for instance, it only reduces air pressure by maybe 20%. Not that much, really.
Okay.
But in science and industry, we create something called ultra-high vacuum, UHV, chambers. These are really sophisticated systems. They can reduce pressure to less than 1/1,000,000th. That's 10 to the minus 12 of atmospheric pressure.
Wow, 1/1,000,000th.
Yeah. Inside a chamber like that, you might only find about 100 particles per cubic centimeter. It's incredibly sparse.
And that's in a lab environment. What about, out there?
Yeah.
In space?
All right, outer space.
Yeah.
That's our best natural vacuum, and it's even emptier. In the vast stretches between galaxies, intergalactic space, you might find just a handful, maybe a few hydrogen atoms per cubic meter. It's just mind-bogglingly empty.
Incredible.
And just a fun little side note on the word itself. Vacuum comes from the Latin vacuous, meaning empty or void. And it's actually one of the few English words with two U's back-to-back.
Huh, never noticed that. Okay, let's dive into this a bit deeper then. How did humans even begin to wrap their minds around this idea of truly empty space, especially when it's so hard to actually make one?
Well, it's a fascinating journey, really. For centuries, the whole idea of a vacuum wasn't just a scientific question. It was a profound philosophical puzzle. Ancient Greek philosophers debated it constantly. You had thinkers like Democritus, part of the atomist school, who argued that a void, an emptiness, had to exist for atoms to move around in. Makes sense, right?
Yeah, logically.
But then you had really influential figures like Plato, who were skeptical, and Aristotle. Aristotle famously championed the concept of horror vacuum.
Horror vacuum.
Yeah, literally, nature abhors a vacuum. He believed any empty space would just instantly be filled. His argument was kind of clever. If a true vacuum existed, motion through it would have zero resistance, right? So things could move infinitely fast or keep going forever. And he just found that idea impossible, illogical.
So for a long, long time, the sort of dominant thinking was, vacuum? Nope. Can't exist. Nature fills the gaps.
Exactly. That view held sway for centuries. Even into medieval times, many scholars, like the Muslim philosopher al-Farabi, flat out rejected the vacuum. Although, interestingly, another scholar, al-Biruni, later pointed out there wasn't actually any observable evidence against it existing. A subtle but important shift. And then there's a really pivotal moment in 1277. The Bishop of Paris, Etienne Tempier, issued these condemnations, basically theological arguments. But in asserting God's absolute power, they implied God could create a vacuum if he wanted to.
Ah, okay. So it cracked the door open, philosophically speaking.
Precisely. It allowed for the possibility of a supernatural void beyond the cosmos, which started to change the intellectual landscape. People could at least consider it.
So the philosophical barrier began to crumble. When did science really step in and say, hey, not only is this possible, we can actually make one?
That really kicks off in the 17th century. It was a huge part of the scientific revolution. In 1643, Evangelista Torricelli, he was working on barometers, studying atmospheric pressure. He accidentally created the first laboratory-sustained partial vacuum. We now call it a Torricellian vacuum. That was massive.
The first actual man-made emptiness?
Well, partial emptiness, yeah. Then, in 1654, Otto von Guericke took it way further. He invented the first proper vacuum pump, and he demonstrated its power with that incredible Magdeburg Hemispheres experiment. You've probably heard of it.
The one with the horses.
That's the one. He pumped the air out from between two large metal hemispheres fitted together, and then teams of horses couldn't pull them apart.
Just from the air pressure outside, pushing them together.
Exactly. An incredible demonstration of atmospheric pressure, and by implication, the power of the vacuum inside. After that, you had Robert Boyle and Robert Hooke improving the pump technology. By the 19th century, with things like mercury displacement pumps developed by August Typler and Heinrich Geissler, scientists could get much better vacuums. And this allowed them to explore new things, like the electrical phenomena in Crookes tubes, the precursors to X-ray tubes and TVs.
Right.
So these experiments really shifted the whole thing from a philosophical debate to something you could actually measure and work with in the lab. It even led to discarding older ideas, like the luminiferous ether, that substance they thought light needed to travel through. Experiments just couldn't find it.
Fascinating. A real journey from impossible to experimentally real. But okay, let's connect this history to the bigger picture now. That historical understanding laid the groundwork, but modern physics. It defines vacuum in really precise and honestly sometimes pretty weird ways, doesn't it?
It really does. Things get much stranger, especially when you get to quantum mechanics. But even in classical physics, the definition is quite strict. Classically, the tightest definition of a vacuum is a region where absolutely everything is zero. No energy, no particles, no momentum, no forces like electromagnetism, nothing. Truly empty in the classical sense.
Okay, devoid of all matter and energy fields. But what about gravity? Can a vacuum still have gravity?
Ah, that's a great question, and it highlights a subtlety. According to Einstein's general relativity, even if you have no matter or energy, what we call a zero-stress energy tensor, space-time itself can still be curved. Think about a black hole that has no electric charge. Outside the event horizon, it's technically a vacuum in terms of particles and fields, but space-time is incredibly warped. You feel strong gravitational effects like tidal forces.
So vacuum doesn't necessarily mean flat, empty space.
Exactly. Gravity can still exist and propagate through it as gravitational waves, for instance. And for electromagnetism, we talk about the vacuum of free space. This is like our perfect baseline medium. In this vacuum, light travels at its absolute maximum speed, that famous C, 299,792,458 meters per second. And crucially, effects just add up. The superposition principle holds perfectly. It has specific properties like permittivity and permeability that define how electric and magnetic fields behave in pure emptiness.
Okay, now here's where I think it gets really interesting. If classical physics basically says a vacuum is empty, what does the quantum world have to say? Because I keep hearing it completely flips the idea of nothing on its head.
It absolutely fundamentally does.
Yeah.
The quantum vacuum is, well, it's mind-bending because it's not empty at all. Far from it.
Yeah.
In quantum physics, a vacuum isn't defined by absence, but as the state with the absolute lowest possible energy, the ground state of whatever quantum field system you're looking at, like QED for electromagnetism or QCD for the strong force.
Lowest energy state.
Okay.
But not zero energy. Not empty.
Not zero, and definitely not empty. The key insight from quantum field theory, and it's backed by experiments, is that empty space is actually this seething, dynamic, fluctuating realm.
Fluctuating? What do you mean by fluctuating? Like, is stuff just appearing?
Sort of, yeah. Think of it like the surface of the ocean. Even on a calm day, there are tiny ripples and waves constantly appearing and disappearing.
Right.
The quantum vacuum is similar. There are these constant vacuum fluctuations where pairs of tiny fleeting virtual particles like an electron and its antiparticle, a positron, spontaneously pop into existence for incredibly short moments.
Pop into existence from nothing.
From the vacuum energy, yeah. They borrow a tiny bit of energy, exist for a fraction of a second allowed by the Heisenberg uncertainty principle, interact, and then annihilate each other, disappearing back into the vacuum.
Wow, okay. And these aren't just like theoretical math.
Oh no, these are real. These vacuum fluctuations have measurable, experimentally verified effects. Things like the spontaneous emission of light from an excited atom it's kicked by these virtual photons, or the Lamb shift, which is a tiny shift in the energy levels of hydrogen atoms caused by interaction with these virtual particles. Even the force between electric charges is slightly modified by this vacuum activity.
So the emptiness is actually mediating forces and affecting particles.
Exactly. There's also this concept of vacuum energy itself, the baseline energy that remains even in the lowest state, and it gets even wilder. Some theories, like string theory, propose a vast landscape of possible quantum vacuum states, each with different fundamental constants and laws of physics. Our universe might just be sitting in one of these many possible low-energy valleys.
Okay, my head hurts a little now. From Aristotle saying no way to space teeming with virtual particles, that's quite a leap. All right, let's bring this back down to Earth, or maybe out to space. From the super theoretical to the practical. Where do we actually find vacuums? How do we measure these different levels of emptiness, and what do we actually do with them?
Right. Well, our best and biggest natural vacuum is, as we said, outer space. It's an incredibly low-density, low-pressure environment. But it's crucial to remember, it's never a perfect vacuum.
Yeah.
Even way out between the galaxies, you've still got those few hydrogen atoms per cubic meter, plus cosmic rays, neutrinos, background radiation.
So not truly empty.
Not truly. And Earth's atmosphere doesn't just stop, it fades out gradually. We often use the Kármán line, about 100 kilometers up, as a sort of conventional boundary for space. The pressure there is incredibly low, something like 32 millipascals. Beyond that, the gas pressure is so low it's almost insignificant compared to things like the radiation pressure from the sun or the solar wind. We start talking about particle density instead of pressure.
And does that very thin atmosphere still matter, say, for satellites?
Oh, absolutely. Even in low Earth orbit, LEO, where the space station and many satellites are, there's still enough atmospheric density, enough particles to cause significant drag over time.
So they have to keep boosting themselves up?
Yep, they need to fire thrusters periodically to maintain their altitude. On the flip side, people are developing concepts like solar sails, which use the tiny push from sunlight radiation pressure for propulsion in that near vacuum.
Clever. And you mentioned background radiation.
Yeah, the whole observable universe is filled with the cosmic microwave background radiation, the afterglow of the Big Bang. It keeps everything at a baseline temperature of about 3 Kelvin, just above absolute zero. So even the emptiest space has this energy field.
Okay, so outer space is a vacuum, but a very specific, not quite perfect kind. How do we actually quantify these different levels of emptiness back here in the lab?
Good question. The quality of a vacuum, as we touched on, is basically about how little matter is left. Lower gas pressure means higher quality. A really key concept here is the mean free path, the MFP.
Mean free path.
Yeah, it's the average distance a gas molecule travels before it bumps into another molecule. Now, in normal air, molecules are constantly colliding. The MFP is tiny, like 70 nanometers.
Yeah.
But as you remove molecules, as you lower the pressure, the MFP gets longer and longer.
Okay.
When the MFP becomes longer than the size of the container you're in, things change fundamentally.
Yeah.
Molecules start hitting the walls of the chamber more often than they hit each other. At this point, standard fluid dynamics doesn't really work anymore. You're in the realm of high vacuum, or UHV, and you have to think about individual particle dynamics.
Ah, I see. So the definition of high vacuum depends on the scale you're working at.
In a way, yes. It depends on the relationship between the MFP and the system dimensions. And we categorize these vacuums into ranges, usually based on pressure. You have low or rough vacuum, medium-high vacuum, HV, ultra-high vacuum, UHV, and even extreme-high vacuum, XHV.
And getting to UHV or XHV sounds difficult.
Extremely. It requires specialized materials like low-carbon stainless steel, all-metal seals instead of rubber gaskets, incredibly thorough cleaning procedures, and often something called a bake-out.
Bake-out, like cooking the chamber.
Essentially, yes. You heat the entire vacuum chamber, sometimes for days, to drive out water vapor and other molecules that might be stuck to the surfaces. It helps achieve those incredibly low pressures. And for units, the standard SI unit is the Pascal, Becquerel di Fitino, which you'll often hear torr, which is based on millimeters of mercury in a barometer. One torr is about 133 pascals.
Right. And measuring these pressures must require different tools, too.
Absolutely.
Yeah.
You can't use a regular pressure gauge for high vacuum. For relatively low vacuums, you might use a capacitance manometer that measures diaphragm deflection. For higher vacuums, you use things like thermal conductivity gauges. A Pirani gauge is a common one, which measure how much heat is carried away by the remaining gas molecules. Fewer molecules mean less heat transfer.
Okay.
And for really high and ultra-high vacuums, you need ionization gauges. These basically zap the remaining gas molecules with electrons, turning them into ions. Then they measure the tiny electrical current produced by these ions.
The fewer ions, the better the vacuum.
Exactly. Hot cathode gauges can get down to about 10 aria torr, which is pretty deep into UHV territory.
Okay, so we can define it, we can measure it, but what do we actually do with all this meticulously created emptiness? What are the uses?
Oh, the uses are incredibly diverse. One huge category is simply protection or creating an inert environment. Think of old incandescent light bulbs. The vacuum, or sometimes inert gas fill, stop the hot filament from oxidizing and burning out instantly.
Right, classic example.
It's also crucial for processes like electron beam welding or cold welding, where you don't want atmospheric gases interfering. And of course, vacuum packing food removing oxygen prevents spoilage. And as we mentioned in high-tech manufacturing, like making semiconductors or optical coatings, you need UHV to keep surfaces atomically clean during deposition processes. Any contamination ruins the device.
So keeping things pure. What else?
Removing obstruction is another big one. Particle accelerators need vacuum so the particle beams don't scatter off air molecules. Same for electron microscopes. The electron beam needs a clear path. It's also fantastic for thermal insulation. Your thermos bottle works because the vacuum between the inner and outer walls prevents heat transfer by conduction or convection.
Ah, the thermos. Yeah.
Vacuum also lets you lower boiling points. This is key for freeze drying, where you remove water from food at low temperatures. It's used in preparing certain adhesives, in chemical distillation, and in metallurgy. Then there are the electrical properties. Vacuum tubes, like old radio tubes or cathode ray tubes in older TVs and monitors, relied on electrons moving freely in a vacuum. Modern high-voltage vacuum interrupters also use vacuum to quench electrical arcs.
And just plain suction, right? Mechanical advantage?
Well, technically it's atmospheric pressure doing the work, but yes, we use vacuum to create pressure differences. The very early Newcomen steam engine actually used condensing steam to create a vacuum, which pulled the piston down. There was even an experimental atmospheric railway designed by Brunel that used vacuum.
No way.
Yep. More practically, vacuum brakes were used on trains for a long time. And in cars, the engine intake manifold creates a vacuum that's used to power the brake servo. That's what makes your brake pedal easier to push.
The brake booster.
Exactly. And in power plants, steam turbines rely on maintaining a strong vacuum in the condenser to maximize efficiency. They use steam jet ejectors or large vacuum pumps to pull that vacuum. It's really everywhere once you start looking.
It really is amazing how many everyday things and cutting-edge technologies rely on carefully controlling, well, nothingness. Now, this does raise an important question. You mentioned how hard it is to get UHV. While vacuum is incredibly useful, creating and maintaining it clearly isn't straightforward. And what about its effects on living things? We see dramatic stuff in movies, but what's the reality?
That's right. Creating a good vacuum is one challenge. Keeping it is another. The biggest enemy is often outgassing.
Outgassing?
Yeah. Basically, all materials have some tendency to release gas molecules, especially when put into a vacuum. Think of plastics releasing volatile compounds or metals slowly releasing trapped gases like hydrogen. Even just water molecules absorbed onto the chamber walls are a huge source.
So the materials of the chamber itself start polluting the vacuum.
Exactly. It acts like a tiny, persistent leak, and it often sets the ultimate limit on how low a pressure you can achieve. Water is usually the biggest culprit in typical high vacuum systems.
And that's why you need the special materials and the bake-out for UHV?
Precisely. You choose materials with very low outgassing rates, like specific stainless steels or ceramics. You ensure everything's incredibly clean, you use metal seals, and the bake-out helps drive off that surface water and other volatile stuff temporarily, allowing the pumps to get ahead. Sometimes they even use cryopumping cooling surfaces with liquid nitrogen to freeze out remaining gases.
Wow. It's a constant battle against escaping molecules. And the pumping itself, how does that work? You said it's not really suction.
Correct. Suction is a bit of a misleading everyday term. You don't really pull a fluid out. What pumps do is create a space with lower pressure, and then the higher pressure outside pushes the fluid into that space. Think about how your diaphragm works when you breathe. It contracts, expands your chest cavity volume, which lowers the pressure in your lungs, and then the higher atmospheric pressure outside pushes air in.
Okay, so it's about expanding volume.
Fundamentally, yes, for many pump types. Positive displacement pumps, like an old-fashioned hand water pump or many industrial vacuum pumps, work by repeatedly sealing off a volume of gas, moving it, exhausting it, and then expanding the cavity again to trap more gas from the chamber. There are other types too, like momentum transfer pumps, turbo pumps that use fast spinning blades to knock gas molecules toward the exhaust, and entrapment pumps, like ion pumps or cryopumps, that trap gas molecules on surfaces.
It sounds like a whole field of engineering in itself.
It absolutely is. It's called vacuum technique. Getting to really low pressures, especially UHV or XHV, requires careful consideration of everything: pump types and stages, seals, chamber geometry, materials, cleaning procedures, leak detection. Even things you wouldn't expect, like how water can slowly permeate through certain metals, or the grain direction in metal flanges affecting sealing.
Good grief. So what are the lowest pressures we can actually achieve?
In the lab, directly measured pressures have reached around 1/10 millitorr. Indirect measurements, like in cryogenic experiments near absolute zero, suggest effective pressures down to maybe 5/10 millitorr. That's incredibly empty, maybe 100 particles per cubic centimeter. Very close to nothing, but still not absolutely perfect.
Still fighting those last few particles. Okay, so we build these amazing systems to get as close to nothing as possible. But what about us, humans, animals? What actually happens if someone is exposed to that kind of environment? Forget the exploding heads in sci-fi.
Yeah, let's debunk that myth right away. Exposure to vacuum is definitely lethal, but it's not nearly as graphic or instantaneous as movies often portray. The immediate effects would be loss of consciousness within maybe 10-15 seconds due to lack of oxygen, hypoxia. Death would follow within a couple of minutes from that oxygen deprivation.
But no boiling blood.
No, your blood will absolutely not boil. The pressure inside your circulatory system, maintained by the elasticity of your blood vessels, is high enough to keep the boiling point of your body fluids well above normal body temperature, 37 degrees C, even in a vacuum.
Okay, if that's one myth down, what is the real danger then, besides suffocation?
The main physiological effect, besides hypoxia, is something called ableism.
Igbulism.
Yeah, it's the formation of gas bubbles, mostly water vapor in your bodily fluids because of the very low external pressure. This would cause significant swelling. The body might bloat to roughly twice its normal size. Circulation would be severely impaired.
Sounds unpleasant, would you? Rupture.
Surprisingly, no. Human skin and tissues are remarkably elastic and also somewhat porous. While the swelling would be dramatic, you wouldn't actually burst open like an overfilled balloon.
Okay. That's slightly less horrifying. Is it survivable?
Brief exposures can be. There were accidents during high-altitude suit testing and also animal studies. NASA did experiments with chimpanzees in the 60s. The data suggests that if you're repressurized within about 90 seconds, you can make a full recovery, although the experience would be traumatic. Much longer than that, and the combination of hypoxia and circulatory disruption from ebulism becomes fatal.
90 seconds. That's a very short window.
Very short. Minor effects would include the moisture on your skin and in your mouth boiling away rapidly, which causes cooling and frost formation. But that's not the life-threatening part.
What about plants or other organisms?
Plants can actually survive low-pressure environments, down to about 1.5 kPa for around 30 minutes. And some microorganisms, particularly extremophiles like tardigrades, water bears.
Oh yeah, those indestructible little things.
Exactly. They can survive vacuum conditions for days or even weeks by going into a dormant state called cryptobiosis. They are true masters of surviving the void.
Tardigrades win again. Okay, so direct vacuum exposure is bad, causes ableism and hypoxia, but maybe survivable briefly. You mentioned suit testing. What's the real danger in space or high-altitude scenarios?
Often, the far more immediate and dangerous threat isn't the vacuum itself, but rapid decompression, a sudden explosive drop in pressure.
Why is that worse?
Because of the air trapped inside your body, primarily in your lungs. If the external pressure drops instantly, the air in your lungs expands violently. If you happen to be holding your breath, or even if the decompression is just too fast for the air to escape normally through your airways, it can cause fatal rupture of the lung alveoli, the tiny air sacs. This is called pulmonary barotrauma.
So it's like an internal explosion.
A catastrophic overpressure, yes. That's why pilots are trained never to hold their breath during a rapid decompression. Even a relatively small, sudden pressure drop, maybe just 13 kPi or 100 torr, which would be harmless if gradual, can be instantly fatal if it causes lung rupture. You can also get other barotrauma, like ruptured eardrums or sinuses, bruising, internal bleeding. The shock itself accelerates oxygen consumption too. Rapid decompression is incredibly dangerous.
That's a really crucial distinction. The speed of the pressure change is key. It makes you appreciate spacesuits and pressurized cabins a whole lot more. Okay, so wrapping this all up, what does this all mean? We've gone from ancient philosophers absolutely fearing the void to quantum mechanics telling us empty space is buzzing with activity. This deep dive into vacuum, it really feels like it challenges our basic understanding of reality.
It absolutely does. It's really a testament to human curiosity and ingenuity, isn't it?
Mm-hmm.
We went from thinking a vacuum was fundamentally impossible, a violation of nature, to not only proving it exists, but developing incredibly sophisticated ways to create it, measure it, and harness it for everything from making light bulbs to manufacturing computer chips, exploring fundamental physics, and even understanding its rather dramatic effects on life. The vacuum isn't just an absence, is it? It's this dynamic stage. It's where fundamental physical processes play out. It constantly forces us to refine what we mean by empty.
Yeah. And when you think about those really mind-bending ideas, like the quantum vacuum fluctuations, these virtual particles just popping into existence from seemingly nowhere, or that theoretical string theory landscape with maybe countless different types of vacuum states, different universes potentially, it really makes you wonder, doesn't it? How much more is our understanding of empty space going to be completely revolutionized in the future? What other nothings are still out there waiting to be discovered that might actually turn out to be, well, everything? Welcome, curious minds, to the deep dive. Okay, so if you hear Jurassic, you probably picture, the thud of a T-Rex, maybe that big brachiosaur reveal from Jurassic Park, right?
Absolutely. iconic images. But the real Jurassic period, that
Yeah.
middle part of the Mesozoic era, it was actually, I think, even more astounding, way more dynamic than Hollywood lets on.
That's exactly what we're getting into. We've gone deep into a really comprehensive Wikipedia entry on the Jurassic. And, well, our mission for you today is to pull out the most fascinating bits, the surprises.
Yeah, the key insights. The goal is you come away from this quickly feeling, pretty well informed about this era that just fundamentally shaped life on Earth
Yeah,
without getting totally lost in the weeds.
exactly. Think of it as your fast track. We're talking continents ripping apart, new oceans forming, giants roaming the land, and some really unexpected creatures popping up.
It's an incredible story.
It really is. So let's unpack it together. First off, that name, Jurassic. It sounds so, I don't know, powerful, almost ancient. Where did it actually come from?
Well, it's quite literally grounded in geography. The name Jurassic, it comes straight from the Jura Mountains. That's a range right on the border between France and Switzerland today.
The Jura Mountains, okay.
And Jura itself apparently goes back to Celtic roots. It means something like wooded mountain.
Wooded mountain, I like that. So it wasn't some, abstract scientific term they just made up.
Not initially, no. It was tied to a place. The first person to really flag these rocks was the German naturalist Alexander von Humboldt back in 1795 on a tour.
Humboldt, right?
He identified these distinct limestone deposits there, called them Jura Kalkstein, Jura Limestone, in 1799. But interestingly, he actually got the date wrong. He thought they were older than they are.
Ah, okay. So he spotted them, but didn't quite nail down their place in the timeline. Who figured that out and actually formalized Jurassic as a period?
That was the French naturalist Alexandre Brongniart. In 1829, he published work connecting Humboldt's Jura limestone to similar rocks over in Britain. That connection was key.
Okay, linking different locations.
Exactly. And that led him to formally coin the term terrain jurassique. That basically established the name and its geological identity.
Got it. So once the period was established, how did scientists start breaking it down? Early, middle, late Jurassic. What tools did they even use back then?
Well, it was a collaborative effort, really. Lots of European geologists, paleontologists working on it. They refined that three-part division, early, middle, late. And a really clever tool they used, ammonites.
Ammonites, those spiral-shelled things.
Yeah, exactly, ancient cephalopods. The thing is, they evolved really rapidly and were found pretty much worldwide.
Yeah.
So their different shapes and different rock layers became like biological time markers.
Index fossils, right?
Precisely. They allowed scientists to correlate rocks across huge distances and figure out which layers were older or younger. Very ingenious, really.
Nature's own geological clock. That's neat. But you mentioned challenges, and there's something really peculiar about the end of the Jurassic, isn't there? Its boundary with the Cretaceous is undefined.
Yeah, it's actually unique and a pretty big headache for stratigraphers, the people who study rock layers. The Jurassic-Cretaceous boundary is the only geological period boundary that doesn't have a formal definition yet.
Wait, the only one? How is that possible?
Well, defining these boundaries precisely requires finding what's called a GSSP, a global boundary stratotype section and point. It's like a golden spike in a specific rock outcrop somewhere that everyone agrees marks the exact start of the next period.
And they can't find one for the end of the Jurassic.
They haven't been able to agree on one. The problem is the fossil markers tend to be quite regional, not globally consistent right at that boundary. And there isn't a really clear worldwide chemical signal in the rocks either. It just makes pinning down that single perfect line incredibly difficult.
Wow. So it just sort of blends into the Cretaceous.
In a way, yeah. It shows how Earth's history isn't always neat and tidy with sharp dividing lines. It can be messy and continuous. It's a fascinating ongoing puzzle.
That geological mystery really underscores the dynamism. And speaking of dynamic, the planet itself was undergoing massive changes. The continents? What was happening with Pangaea?
Oh, huge changes. The early Jurassic is when the supercontinent Pangaea really started to break apart. That giant landmass that had fused together earlier,
All the land in one place.
well, it began rifting, splitting into two main chunks. Laurasia up north, that's future North America, and Eurasia and Gondwana down south, future South America, Africa, Antarctica, Australia, India.
So it's like this massive geological divorce happening.
Pretty much.
Yeah.
And this massive split directly led to new oceans opening up. The big one being the North Atlantic. It started forming right then.
Incredible. New oceans appearing, and the climate was changing too, wasn't it? Very different from today.
Very different. Generally much warmer. Estimates are around 5 to 10 degrees Celsius, hotter globally than now.
Wow.
5 to 10 degrees.
Yeah, and CO2 levels in the atmosphere were probably like 4 times higher than today. And crucially, no permanent ice caps.
Yeah.
Anywhere. Not at the poles, nowhere.
No ice caps at all.
None. In fact, forests grew surprisingly close to the poles. They'd have warm summers, but probably cold, maybe even snowy winters, but still forests.
That paints a really different picture of the planet. But was it warm and humid everywhere?
No, not uniformly. Despite the overall warmth, there were actually pretty large arid, dry zones in the lower latitudes, say around 40 degrees north and south of the equator. Big deserts.
So belts of dryness even in a generally warmer world.
Exactly, which is, again, quite different from today's climate patterns. Shows how heat and moisture get distributed differently under those conditions.
And within this warmer, shifting world, there was this major event, the Torsion Oceanic Anoxic Event.
Toei-Isi. Sounds pretty dramatic.
It was, yeah. The 2IUA happened around 183 million years ago in the early Jurassic. It was basically a global environmental crisis.
A crisis? How so?
You had widespread oceanic anoxia, meaning huge parts of the ocean lost their oxygen, plus ocean acidification and a spike in global temperatures on top of the already warm climate. Lack of oxygen, acid oceans, more heat. That sounds devastating for marine life. What could cause something like that on a global scale?
The main suspect is massive volcanic activity, specifically huge eruptions from what we call the Karoo-Ferrar large igneous provinces. Think vast floods of lava pouring out across southern Gondwana.
Wow, massive volcanoes.
Yeah, and these eruptions would have pumped enormous amounts of CO2 and other greenhouse gases into the atmosphere and oceans. That's what likely drove the anoxia and acidification.
And the impact on life.
It was severe, especially for marine life that builds shells or skeletons from calcium carbonate, like certain plankton and brachiopods. There were significant extinctions in those groups. It really shows how tightly linked the planet's systems are, volcanoes impacting ocean chemistry, impacting life.
It really does. A chain reaction. You know, thinking about that event, massive CO2 release, ocean acidification, warming. It sounds disturbingly familiar. What lessons can we maybe draw from the TOE for today?
That's a really important question, isn't it? It shows us just how sensitive ocean ecosystems can be to rapid changes in atmospheric CO2. It's like a geological case study demonstrating the potential consequences, widespread oxygen loss, acidification, extinction that can happen when carbon cycles are drastically perturbed. It underlines the risks we face now.
A sobering thought from deep time. Okay, so shifting from climate crises to life on land. Obviously, the Jurassic is the age of dinosaurs, but what about the plants? What kind of world were these dinosaurs actually living in?
Right. The flora is crucial. The landscape wasn't like today with flowering plants everywhere. It was dominated mostly by ferns and various types of gymnosperms. Those are non-flowering seed plants.
Gymnosperms. Okay, look, what would I recognize if I, took a hypothetical stroll?
Well, you definitely see lots of conifers. Ancestors of modern groups were around. Things like Araucaria related to the monkey puzzle tree, they were actually really widespread then. Also the cypress family, Cupressaceae. And an extinct family called Caryopodiaceae was super abundant.
Okay, conifers, cypresses.
Yeah.
What else?
Ginkgos. Ginkgo biloba, the living fossil tree. Well, back in the Jurassic, the ginkgos were much more diverse. Lots of different species adapted to various climates, especially across Eurasia. And then there were the Benetiles.
Benetiles. Never heard of them.
They're extinct now, but they're really interesting. They sort of look like cycads in terms of their leaves, but they had these incredibly complex reproductive structures. Almost like flowers, but not true flowers.
Flower-like structures, before actual flowers evolved.
Exactly. And what's really cool is that some scientists think insects might have pollinated them, which suggests these really intricate plant-insect partnerships, the kind we associate with flowering plants later on, might have started evolving much, much earlier.
Whoa! Insect pollination way back in the Jurassic, before proper flowers. What does that, imply for how coevolution works?
It really pushes back the timeline, doesn't it? It suggests that the basic playbook for specialized pollination, maybe even seed dispersal by animals, was being developed long before the angiosperms, the flowering plants, took over. It shows this deep, ancient history for those kinds of ecological relationships.
That's amazing. So this was the green backdrop. How did the dinosaurs really rise to dominance within this world?
Well, dinosaurs had already diversified a bit in the late Triassic, but the key moment was the extinction event at the end of the Triassic. That wiped out a lot of other large reptiles and opened up ecological space.
Ah, so the extinction wasn't bad news for everyone.
Not for the dinosaurs, no. It was almost like a starting gun. In the early Jurassic, they just exploded in diversity and abundance. They quickly became the dominant animals on land.
So that extinction cleared the stage, and the dinosaurs just stepped right into the spotlight. How did that play out? Like for the famous meat eaters, the theropods?
It was definitely their time. Theropods radiated out incredibly. And this leads to one of the most remarkable evolutionary stories, the origin of birds. The very first stem group birds appear right here.
You mean Archaeopteryx?
Exactly. Archaeopteryx lithographica,
Yeah.
found in late Jurassic rocks in Germany. It's that perfect transitional fossil, clearly showing its dinosaur ancestry, but with feathers and adaptations for flight.
Such an iconic fossil. But it wasn't just the theropod line leading to birds that was doing interesting things, right? What about other groups?
Not at all. You had early ornithischians, the sort of bird-hipped dinosaurs like Lesothosaurus, and then a really surprising discovery came from Russia, from the Middle Jurassic, a dinosaur called Culindrodromeus.
Calindrodromeus, what was special about it?
It had proto-feathers, simple filament-like structures covering its body, and it was an ornithischian, not closely related to the bird lineage at all.
Wait, proto-feathers on a completely different type of dinosaur. That changes things, doesn't it?
It massively changes things. It challenges the old idea that feathers were just a feature of the theropods leading to birds.
Yeah.
It suggests that feathers, or at least feather-like coverings, might have been much more widespread among dinosaurs.
Yeah.
Maybe even an ancestral trait for many of them.
Wow. So maybe lots of dinosaurs were fuzzy. Are we rethinking feathers entirely now?
We absolutely are.
You
It opens up all sorts of questions about maybe thermoregulation or display, camouflage. It suggests these structures could have evolved much earlier and for different reasons before being co-opted for flight. It's a really active area of research.
Fascinating. And of course, we can't talk Jurassic dinosaurs without talking about the giants.
The sauropods, yes. They became the dominant large herbivores, just massive animals.
Right.
And some of them reached truly colossal sizes. We're talking the largest land animals ever to have lived.
Like who?
Well, things like Mamenchisaurus, famous for that ridiculously long neck. They were just these enormous plant processing machines, fundamentally shaping the ecosystems they lived in just by being so huge.
Incredible. So dinosaurs hitting their stride feathers, flight, gigantic size. But land wasn't the only action. What about other critters? Crocodilomorphs, for instance. We picture crocodiles today, but Jurassic ones were different.
Oh, incredibly different and diverse. What's amazing first is that crocodilomorphs, that's the broader group, including crocs, gators, and their extinct relatives, were the only major group of pseudoseuchins, another branch of archosaurs, to actually survive the Triassic-Jurassic extinction.
So they were survivors.
Big-time survivors. And afterwards, they just radiated into all sorts of lifestyles you wouldn't expect.
Like what kind of unexpected lifestyles?
Well, some stayed terrestrial,
Yeah.
sure, but many became fully aquatic marine predators, like dolphin-shaped or shark-shaped things hunting in the oceans. And maybe the most surprising, we have evidence of an early herbivorous crocodilomorph.
You're kidding. A
Yeah.
plant-eating croc relative.
Not kidding. An unnamed protoseuchid found in Arizona seems to have been eating plants.
That just blows the modern croc image out of the water. A vegetarian croc relative. What does that tell us about how adaptable they were back then?
It tells us they had incredible ecological flexibility. They weren't locked into the ambush predator role we see today. They were experimenting, trying out different diets, different habitats. It shows a level of evolutionary creativity we just don't usually associate with them.
Really changes the picture. Okay, what about the skies? Pterosaurs ruled the air then, right?
Absolutely. Pterosaurs were the undisputed masters of the Jurassic skies. And they were really diverse, too, especially in how they fed.
How so?
You had long-tailed ones like ramphorhynchids, probably snatching fish from the water, then tiny fuzzy ones called anurognathids, maybe darting after insects like bats do today. And then you get really specialized ones like the stenotchasmatids. Stenotchasmatids, like Stenotchasma. They had these amazing jaws lined with hundreds of fine needle-like teeth. The theory is they were filter feeders.
Filter feeding, like a flamingo or a whale, but a flying reptile.
Exactly. Scooping up tiny organisms from the water. It just shows the incredible range of ecological niches pterosaurs were filling.
Wild. Okay, flying filter feeders. What about our own relatives? Mammals, or mammaliaforms. They were around, but small, right?
They were definitely around, yes. Mammaliaforms, the group including true mammals and their closest extinct kin, they diversified quite a bit during the Jurassic, but yeah, they generally stayed small, living in the shadows of the dinosaurs, ecologically speaking.
But were they just hiding or doing interesting things?
Oh, incredibly interesting things. They showed this amazing burst of early evolutionary creativity, even if they were small.
Like what? Give me some examples.
Okay, how about Castorocata? Found in China, Middle Jurassic.
Yeah.
It was basically aquatic, like a platypus or otter, with a flattened tail, probably webbed feet, adapted for swimming.
A swimming mammal relative back then. Cool.
Right. Or gliding forms, the Velaticotherini. They had membranes stretched between their limbs like modern flying squirrels, gliding through the Jurassic forests.
Gliders, too. Okay, what else?
And Fruitifossor, from the Morrison Formation in North America. It had these robust claws and features suggesting it was a digger, specialized for eating insects, maybe termites, kind of like a primitive anteater or a aardvark.
Wow, so swimmers, gliders, diggers, these early mammal relatives were already trying out all these specialized lifestyles way back then.
Absolutely. They weren't just generalized little shrew-like things. They were experimenting. And there's another key find, Juramaya.
Juramaya, right. What's its significance?
It's considered a very early eutherian mammal that's the lineage leading to placentals, like us. Finding it in the late Jurassic pushed back the estimated split between placentals and marsupials by like 35 million years.
35 million years earlier.
Yeah. It means the fundamental divisions within modern mammals happened much deeper in time, right there during the age of dinosaurs, than we used to think.
Small, but already setting the stage for later mammal dominance. Incredible. Okay, finally, let's quickly dive back into the oceans. Marine invertebrates. How did they do after that big Triassic extinction?
Well, the recovery was slow, especially for things like coral reefs. They took a massive hit at the end of the Triassic, and complex reef ecosystems didn't really bounce back in a big way until the late Jurassic.
So a slow recovery for reefs. But what about other groups?
Ammonites, we mentioned them as index fossils, they underwent an explosive diversification, just radiated into countless forms, which is why they're so useful for dating Jurassic rocks. And another interesting group, crabs.
True crabs appear then.
The first ones, yeah. Eocarcinus precursor shows up in the early Jurassic. And by the later Jurassic, crabs were becoming more common, moving into new places like reefs, maybe trying to avoid getting eaten by all the new predators evolving in the seas.
It just seems like every corner of the planet was buzzing with change and evolution. And these Jurassic events, they didn't just happen and disappear, did they? They left echoes we still see today.
Absolutely. The geology of the Jurassic has huge economic importance even now. Many of the rocks formed back then, like a formation called the Kimmeridge Clay in Europe.
Kimmeridge Clay.
Yeah, it's what's known as a major source rock for oil and gas. A lot of the oil in the North Sea, for instance, originally came from organic material deposited in those Jurassic seas. Same for parts of the Middle East, like the Arabian Intrashelf Basin. Some of the world's biggest oil fields have Jurassic origins.
Wow. So the energy we use today is partly thanks to decomposed Jurassic life. It's quite a legacy. And it wasn't just Earth's own processes shaping things, right? Impacts from space.
That's right. We know of some significant asteroid or comet impacts during the Jurassic. There's the Murakweng crater in South Africa and the Puchesketunki crater in Russia. Both are large impact structures dating from this period.
So cosmic collisions were part of the story, too.
Definitely. They're a reminder that Earth history is influenced by extraterrestrial events, as well as internal geological forces. Sometimes those impacts can have really profound effects on life.
It really paints a picture of a world constantly in flux, shaped by forces from within and without. Just incredible to think about.
It really is. The Jurassic was just this period of such intense dynamism. You had the continents rearranging, the climate shifting dramatically, and life responding with just astonishing innovation on land, sea, and air.
Understanding this deep history, it really does give you a new appreciation for how long and complex our planet's story is and how connected everything is, Geology, climate, life.
Absolutely. And maybe that brings us to a final thought for you, our listener. When you consider everything we've talked about, the huge climate shifts, the extinctions, the incredible resilience, but also the vulnerability of life shown in the Toei, what do you think are the most important lessons that Jurassic holds for us today? Especially thinking about the resilience and fragility of life as we face our own period of rapid environmental change.
That's a really powerful question to ponder, something to definitely think about. Thank you for joining us on this deep dive into the truly awesome Jurassic period. We'll see you next time.